Good evening, sirs. In this session, we will discuss about the liquefaction of soils. Liquefaction is a phenomena in soils. This is included in the soil mechanics syllabus. Actually, this is a topic in earthquake geotechnical engineering because the liquefaction phenomena occurs during earthquake. Liquefaction means soil will behave like a liquid. So the behavior of liquid and soil, if we compare, the soil is not going to flow like a liquid, but on certain aspect the soil is going to function like a liquid. So what is that aspect? That is what we are going to discuss in this session. Liquids doesn't have a shear strength. That is why it flows. That is why it is not capable of taking any loads. But the soil is having a shear strength. This shear strength is a very important topic in soil mechanics because in any building material, the strength determination, strength assessment is very important. For example, in steel, we focus on tensile strength. In concrete, we focus on compressive strength. In soils, we focus on shear strength. This shear strength concept was evolved by Mohr-Coulomb, and the Mohr-Coulomb expression is given by an equation tau is equal to C plus sigma tan phi. The tau is the shear strength, C is the cohesion, sigma is the effective stress, tan phi. Phi is the friction angle of the soil. This expression was given initially and later it was modified with a more focus on sigma, and it is given as tau is equal to C plus sigma dash tan phi. So this sigma dash is the effective normal stress. This is going to be the main focus of our discussion today. The effective stress concept was initially introduced by Karl Terzaghi. He is called the father of soil mechanics. So what he says as the effective stress, suppose if we construct a building on the ground surface, the load of the building goes down. This he called as the total stress, and this total stress he divided into two components. One component is the effective stress, another component is a neutral stress. For example, if we take a container like this, this container is having soils. So this soil is a saturated soil. This soil is a saturated soil. Saturated soil means the soil grains are there, and in between the soil grains there is a void. The voids are totally filled with water. That is why it is called saturated soil. In the saturated soil, if a load is transferred like this, the load transfer at the top comes to the bottom. So whatever the load we have given, that is called the total stress. So this total stress Terzaghi has given by a symbol sigma. The same total stress comes to the bottom also. So whatever the stress given at the top comes to the bottom also. But in between, some portion of the total stress is passing through the soil grains. The remaining portion of the total stress is passing through the water in the voids. So what he has given is the sigma total stress consists of two portions. sigma is equal to sigma dash plus u. So the stress which is passing through the soil grain is called the intergranular stress. The stress which is passing through the soil grain is called the intergranular stress, and the stress which is passing through the water is called the pore water pressure. So this intergranular stress was called by Terzaghi as the effective stress. And the pore water pressure was given by Terzaghi as the neutral stress. So this stress which is passing through the soil grain is the effective stress, and the stress which is passing through the water in the pores is called the neutral stress. These two words he coined with more cautiously and with more emphasis on the phenomena. He called this as the effective stress because it is effective in building the shear strength. He called this pore water pressure as the neutral stress because it is not contributing or damaging the shear strength. It is neutral in its behavior. That is one meaning. Another meaning is water is a neutral liquid, so he called it as a neutral stress. So this effective stress is what is given in this Mohr Coulomb expression as the tau is equal to sigma dash tan phi. So this effective stress concept of Terzaghi was explained by a small model . So this model is famously called Terzaghi's one-dimensional model. So if we apply a load, the load is transferred, and if we are giving small pores in the piston, the water expels through that. That shows the reduction of effective stress is transferred as the reduction of neutral stress is transferred as the effective stress, and that is why this piston is going down. This model of Terzaghi is called the one-dimensional consolidation model of Terzaghi. This mechanical model of consolidation theory is very helpful for us in understanding this C plus sigma dash tan phi model. Now this Coulomb's equation is a common equation for all soils. Tau is equal to sigma dash tan phi. Suppose if the soil is only cohesion alone, the friction angle is 0, then this equation can be reduced as tau is equal to C. Suppose if the soil is a sandy soil, this equation can be reduced as tau is equal to sigma dash tan phi. So this liquefaction phenomena which we are discussing now happens only in soils, only in sandy soils. So this sandy soil phenomena we are going to discuss now. In this equation, tau is equal to sigma dash tan phi. If the effective stress becomes 0, shear strength also will become 0. Is there any possibility that effective stress becomes 0? That is being explained in this expression, sigma is equal to sigma dash plus u. So if we are applying a load, that is total stress, that is divided into two components, effective stress and u is the neutral stress. Now if the total stress remains constant and u is increasing by some means, sigma dash is going down. For example, sigma is equal to 20, this may be 16 plus 4. Suppose by some means this 4 is becoming 2, naturally this 16 becomes 18. So the phenomena is the neutral stress increases, effective stress goes down alternatively. That is also possible. For example, the same 20 may be equal to 14 plus 6. So if the neutral stress is increasing, effective stress is going down. So what this liquefaction phenomena is, the neutral stress, if it go on increasing, without the increase of the total stress, a possibility will come where the effective stress will become 0. For example, this 20 is equal to 0 plus 20. This is an extreme case in which the neutral stress is increasing without causing any change in the total stress, then the effective stress will become 0. If the effective stress becomes 0, shear strength also will become 0. So this concept was explained by Terzaghi, and this is the reason for liquefaction. In fact, what are the reasons for which this can happen? That is, the neutral stress is increasing to a greater extent without causing any change in the total stress. This phenomena may happen in a river bed. Suppose in a river is there are two rivers are there, in between there is a sandy soil. If there is a flooding in both the rivers, the water level will increase. Because of the water level increase, the pore water pressure will increase. As the pore water pressure increases, effective stress becomes 0. If the effective stress becomes 0, shear strength becomes 0. This is the cause for the phenomena of quicksand. So this quicksand phenomena is in fact the origin for the study of liquefaction. The quicksand may happen in any of the river beds. For example, near our Trichy, the Mukkombu, the quicksand phenomena has been there and it has occurred so many times. So what is this quicksand is, it will look like a sand, but if you go nearer to that, suddenly a person can go down. Because it looks like a sand, but it is behaving like a liquid. As the shear strength is 0, it will function like a liquid. This is what we call in Tamil and all as a Pudai Manal. But it is not going to suck any person who is going inside. That is a myth. But as the shear strength is 0, it is like a liquid. As a person cannot walk on the liquid, a person cannot walk on quicksand also. Once he steps into the quicksand, he will suddenly go down. That is the phenomena of quicksand. The main dangerous aspect of quicksand is this will not happen in a particular place and a particular time. The location will vary from time to time. Because of the variation in the river water level, the quicksand will happen in one place at one time and it will happen in another place at another time. So that is why normally these alert boards or danger boards are kept in so many places. So this is the phenomena of quicksand. The same thing may happen in any saturated soil during earthquake. Suppose if the same phenomena like quicksand happens in sand because of earthquake, that is what is called liquefaction. Suppose if we have a building, below the building there are certain clay soil is there, beneath that there is a sand. This sand is a saturated sand. What happens during earthquake is, for a fraction of a second, the pore water pressure suddenly increases. As the pore water pressure suddenly increases, the shear strength becomes 0. As the shear strength becomes 0, it is like liquid. So within that fraction of a time, the entire building will collapse inside. So a building cannot stand on water. This may happen for a very small duration, small fraction of a time, but this is sufficient enough for the collapse of the entire structure. So this phenomena will happen in any saturated sand at any particular earthquake. So this phenomena is a very, very dangerous phenomena. In fact, there is no structural design for liquefaction. We cannot design a building for liquefaction. We can design a building for earthquake. Depending upon the earthquake magnitude, depending upon the vibration it's going to come, we can put the reinforcements in the building. But for liquefaction, a building cannot be designed. So what's the best possible option is certain important buildings need not be constructed on the liquefied site. So for that, what people have studied is we have to identify certain areas which can happen in earthquake, and in that place the earthquake also very frequent and the earthquake magnitude is also very frequent in that particular zone. So depending upon the zonation, depending upon the magnitude of earthquake comes, this soil will liquefy or not. This study was started in 1950 by Bolt and Seed. So they have studied so many places where liquefaction has happened, and they have collected the soil data. They have collected the earthquake magnitude also in a particular spot where the liquefaction happened. So this is one data. Like that, Bolt and Seed has collected thousands of points and he has created a chart. So this chart is being used till now. So if we are doing certain soil test here, for particular soil, this soil will liquefy for this particular magnitude. So this study will be helpful to identify for a particular soil to liquefy or not for a particular magnitude of earthquake. If we could have predetermined that certain important buildings like hospitals, like a power generation plant can be avoided in that. This is one use of liquefaction phenomena. Suppose if already a structure is there in that particular place, strengthening aspects can also be done. So that is also an important usage of liquefaction assessment. However, the study of liquefaction is a very important phenomena in soils, and it is an advanced study also because this Bolt and Seed concept is based upon the statistical aspects. We are not determining whether a soil will liquefy or not scientifically. We have collected only certain data from the past history. Based on we are reinterpret in this soil data. There is no scientific study. That is why liquefaction is considered as one of the very important research topic in geotechnical engineering. Could have predetermined that certain important buildings like hospitals, like a power generation plant can be avoided in that. This is one use of liquefaction phenomena. Suppose if already a structure is there in that particular place, strengthening aspects can also be done. So that is also an important usage of liquefaction assessment. However, the study of liquefaction is a very important phenomena in soils, and it is an advanced study also because this Bolt and Seed concept is based upon the statistical aspects. We are not determining whether a soil will liquefy or not scientifically. We have collected only certain data from the past history. Based on we are reinterpret in this soil data. There is no scientific study. That is why liquefaction is considered as one of the very important research topic in geotechnical engineering. Like liquefaction, another important property in soils, which is also included in the undergraduate syllabus, is the earth pressure concept. So this earth pressure concept can also be understood with the help of the behavior of liquid. In that way, this is also related to liquids. Suppose if we have a water tank, so in this water tank, if the water is full, so the pressure of water at the bottom of the water tank is given by the expression gamma W into H. So So this h is the height of the water tank, gamma w is the unit weight of water. So gamma w will be in kilonewton per meter cube, h will be in meters. So the pressure, the downward pressure is kilonewton per meter square. So this is a basic study. In the same water tank, suppose if I make a hole here, on the lateral side, so the water will come out with some pressure. This water pressure also having a coefficient of gamma w into h. So the vertical pressure also gamma w into h. On the same place, if we make a hole lateral direction, that is also gamma w into h. Suppose if I make a hole in the middle, the water will come like this. So this pressure will be gamma w into h1. So this distance is h1. So this we study only to understand that the vertical pressure and horizontal pressure is same in case of liquids. Suppose if we find a ratio sigma h divided by sigma v, this is equal to 1. So sigma v is the vertical pressure, sigma h is the horizontal pressure. So both are same. That is why this ratio sigma h divided by sigma v is equal to 1. Let us consider the same experiment in soils. If we fill with soils, so now the same tank is filled with soil. In this condition, the density of the soil is, let us say, gamma d. Gamma d is the density of the soil, h is the height of the tank. So the vertical pressure is same, gamma d into h. So gamma d into h is the vertical pressure, like gamma w into h in water. Suppose if I make a hole here in the lateral direction, the soil also will come like a liquid, but the pressure is different. So what the experiments indicated is, so if the pressure comes here, it is gamma d into h multiplied by a factor called k. So it is k into gamma d into h. It is not like water, where the vertical pressure and the horizontal pressure is the same. Here vertical pressure is gamma d into h, horizontal pressure is k into gamma d into h. If we find a ratio, as we have done earlier, is equal to so k is the coefficient of earth pressure which is less than 1 normally. So the vertical pressure and horizontal pressure, if we compare, the vertical pressure is more, horizontal pressure is less. But it is related to vertical pressure. That is why this is k into gamma d into h. Gamma d h is the vertical pressure. So we can write like this: sigma h is equal to k into sigma v. So this determination of k, called the coefficient of earth pressure, is an important topic in this earth pressure unit. If we know the value of k, lateral earth pressure can be calculated. Once we know the lateral earth pressure, this is an important input for the designing of retaining walls. In designing retaining walls, we have to design the wall for the earth pressure coming out. So what is the pressure the soil is going to give to the retaining wall? That we can able to decide only if we know the magnitude of k. The k can be calculated only if we know certain earth pressure theories. To determine the value of K, so many theories have come. Among that, Rankine's theory is very simple and very popular. What he has derived is K is equal to K is equal to 1 minus sin phi divided by 1 plus sin phi. This same K Rankine has given in 3 different cases. If the retaining wall is stationary, he called it as a wall at rest. Then he called his earth pressure coefficient at K naught. If the wall is moving away from the backfill, suppose this is the retaining wall, this is the soil. If the wall is tilting like this, that is, the wall is moving away from the backfill. Backfill is the soil here. This condition he called it as the active condition. If the wall is moving towards the backfill, that condition he called it as the passive condition. So he derived all his equations for active condition as well as passive condition. So active condition is if the wall is moving away from the backfill, it is the active. If the wall is moving towards the backfill, it is passive. So this active condition he considered as a Ka. His coefficient is called Ka and this is Kp. So he derived the equations for Ka and Kp. The equations are Ka is equal to 1 minus sin phi divided by 1 plus sin phi. Kp is equal to 1 plus sin phi divided by 1 minus sin phi. So these two simple expressions, the coefficient of earth pressure at active case is 1 minus sin phi divided by 1 plus sin phi. Coefficient of earth pressure at passive condition is 1 plus sin phi divided by 1 minus sin phi. Both these conditions he derived with the basic definition of the soil at plastic equilibrium. So he defined what is plastic equilibrium also. So when a soil is failed, then that cannot be analyzed. Before failure, the soil is in elastic condition. What he has identified is soil at the verge of failure or at the threshold of failure, he has to analyze the soil. That condition he considered as the plastic equilibrium. So plastic equilibrium of soil is the soil at which it is not yet failed, but it is at the verge of failure. At that failure, what is the stress components? These stress components he analyzed with the help of the Morse circle, and the Morse circle is very helpful for him to have his formula of 1 minus sin phi divided by 1 plus sin phi in active case, and the 1 plus sin phi and 1 minus sin phi for passive case. The earth pressure at rest can be analyzed with the help of elastic equations. So that is very common and very simple, but these cases which was analyzed by Rankine using plastic equilibrium is very popular and is very practical also. So these expressions can be helpful to identify the magnitude of earth pressure on a retaining wall. The earth pressure at retaining wall can be studied under different cases. For example, if there is a retaining wall and it is having soil like this, the height is h. The soil is a dry soil, dry sand, let us say. This is dry sand. So the pressure distribution can be drawn like this. This is Ka gamma dH. As we have already discussed, this is Ka gamma dH. This Ka gamma dH is the pressure at the bottom at the depth of H. What is the total sigma H? This is the half Ka gamma dH square. So, the area of the pressure distribution diagram, that is half Ka gamma dH square, is the total horizontal thrust on the wall. This acts at a distance of h by 3 from the bottom. This is one case. Suppose if the soil is a submerged soil, this is another case. Suppose if the soil, the same soil is in a submerged state. This is a submerged soil where the water table is at the ground level. For this, the pressure distribution diagram can be drawn like this. This is Ka gamma submerged into H. So, the soil is a submerged soil. So, it is Ka gamma submerged into H. This is the lateral earth pressure of the submerged soil alone. But here the water also will exert a pressure. That can be given by an additional triangle like this. That is gamma W into H. As the water does not have the difference between the horizontal pressure, the pressure distribution diagram is gamma W into H. There is no Ka or Kp for water. If we want to know what is the total thrust because of the submerged soil on the wall, is this sigma H. So, this sigma H is equal to half Ka gamma submerged into H square plus half gamma W H square. The area of this pressure distribution diagram is half Ka gamma submerged H square. This is half gamma W H square. So, the first part is because of the submerged soil, the second part is because of the water. This is the second case normally occurs. Sometimes the soil will be partially submerged. This is another important case. H1 is the soil which is not submerged. This may be a dry soil. This is a submerged soil. So, this is the water table. So, here the density of the soil is gamma D, here it is gamma submerged. For this, the pressure distribution diagram can be drawn like this. First, let us take for this dry soil, it will come like this. This is Ka gamma D H1, very important. The same pressure will come down also, it will be like this. This is Ka gamma D H1, same pressure which is coming down. Now, let us consider the second layer separately. This is Ka gamma submerged H2. So, this Ka gamma submerged H2 is the horizontal stress because of the submerged soil. In addition to that, for the second layer, we will have a thrust from the water also. Gamma W H2. If we add the pressure of all the diagrams, we will get the total thrust on the wall, that is the sigma H is equal to half Ka gamma D H1 square plus Ka gamma D H1 H2 plus half Ka gamma submerged H2 square plus half gamma W H2 square. Very important. There are 4 components. First part, half Ka gamma D H1 square is the vertical pressure because of the top layer. Second thing, Ka gamma D H1 into H2 is the horizontal stress because of the submerged soil, but it is transferred to the second layer. And the next one is the half Ka gamma submerged H2 square is the horizontal stress because of the submerged soil. The fourth part is the half gamma W H2 square is the horizontal thrust because of the water. If we add all the 4 components, we will get the total horizontal thrust on the retaining wall. And where it will attack, that is on the, we have to find out the center of area of all the 4. At that point it will act. That is normally at an Y bar. We have to find out the centroid area of all the diagrams, and at that point it will act. This is a third important criteria. The next fourth one, if the height of the wall is h, if we have a weight of q, this is a surcharge load is acting on the wall surface. On this case, the pressure distribution diagram will be like this. This is KAQ. Q is the vertical thrust, it is converted into KAQ. In addition to that, we will have like this. This is Ka gamma D H1. This is the dry soil. So, what the total thrust is sigma H, which is equal to KAQH plus half Ka gamma D H1 square. So, there are 2 components here. One is the first component, that is because of the surcharge weight. Another one is the second component, that is because of the surcharge, the soils. So, the KAQH is because of the surcharge load, and half Ka gamma D H1 square is because of the soil. Suppose if the Q, this surcharge is there in different cases, as we have already discussed, same thing can be superimposed. These are all the preliminary cases which are very important in retaining wall design. Suppose in the same cases, if we have 2 different soils with 2 different friction angles, then we will have Ka value will be different. For example, let us have like this. This is soil 1, this is soil 2. This is having a height of H1, this is having a height of H2. This value is Ka1, this value is Ka2. So, this is a different soil, this is a different soil. Ka1 is different, Ka2 is different. In this case, what will be the pressure distribution diagram? Let us take the first layer, it will be like this as usual. Ka gamma D H1. The important point to be understood here is this gamma D H1 is a vertical pressure which is coming down. When it is coming down, it is converted into horizontal by the second soil. Suppose Ka2 is greater than Ka1, the pressure distribution diagram will be like this. This will be Ka2 gamma D H1, Ka1. So, gamma D H1 coming down, it is being converted into horizontal by Ka2. So the pressure is Ka2 gamma d H1. Since Ka2 is greater than Ka1, it is an extended rectangle. Now let us come to the second layer. It will be like this. This is Ka2 gamma d H2. So the total earth pressure diagram will be like this. Half Ka1 gamma d H1 square plus Ka2 gamma d H1 H2 plus half Ka2 gamma d H2 square. So half Ka1 gamma d H1 square is because of the topsoil. If it is coming down, it is becoming rectangle. That pressure is Ka2 gamma d H1 H2, and the third one is because of the second soil, that is half Ka2 gamma d H2. This is for two soils. The same can be extended for three soils. In the same diagram, if we have a surcharge load, accordingly it has to be changed. If we have a water table, accordingly it has to be changed. Suppose if the Ka2 is lesser than Ka1, this diagram, this will be coming this side. So these changes can be done very easily if you understood these basic pressure distribution diagrams of earth pressure. So the types or the cases we have discussed is entirely for a sandy soil. Suppose if the backfill surface is a clayey soil, then the pressure distribution diagram will be different. There certain soils will be considered as in a tension zone and certain other soils will be in compression zone. So the pressure distribution diagram itself will come like this. Suppose this is a soil. This soil consists of both cohesion and friction angle. It is not the pure sandy soil. It is having both cohesion and friction angle, and this is the retaining wall. If the wall is moving away from the backfill, that is the active case. So in active case, the pressure distribution diagram will come like this. So if the wall goes like this, up to this height, this portion is called the tension zone, this is the compression zone. So the soil will not move along with the wall. When the wall is moving towards this side, because of the pressure of the soil, in a sandy soil, the entire soil mass will come along with the wall. On a particular stage, there is a failure. At that particular stage is called the plastic equilibrium. On that state, the stress was determined as we have already explained. But in the case of C5 soils, where the soil is both cohesion and friction, it will this particular depth of soil will not come along with the wall. So that portion is what is called the tension zone, and the remaining portion is called the compression zone. For this, the expressions were derived like this. This is the 2C divided by gamma. For this depth, the soil will not move along with the wall. This portion is what is called the tension crack. So it will come like this. So this soil is not moving along with the wall, but the wall is moving. As a result, what happens is there is a small crack here. That crack is what is called the tension crack. So the total earth pressure now is only because of the compression zone. This tension crack concept leads to the depth of cut. For example, in a sandy soil, if we excavate the soil, we cannot excavate it vertically. It will collapse like this. In a seashore, if we excavate, it will come like this. We cannot have a cut like this. But in a C5 soil, where the soil is a mixture of sand and clay or pure clay, we can excavate the soil like this. That is why we are able to excavate the ground and we are constructing the foundations. So this excavation which is made on the ground, this clay soil or a mixture of sand and clay is capable of having a vertical cut up to some depth. Up to what depth we can confidently go on? For that, this depth of cut or this tension crack is helpful. What we found is this depth of cut is 2 times of the tension crack. So any soil will have a vertical cut without any bracing, without any support. It will stand up to the 2 times the tension crack. So it is 4C divided by gamma. So for a soil, particularly for a pure clay soil, the depth of cut is the 4C divided by gamma. If the soil is a clay and soil, 4C divided by root K, gamma root K. We can include K also. Here also 2C divided by gamma root K. So this depth of cut is a very, very important concept in soils, because if we go beyond that depth, then it has to be cut with the supports. Otherwise there is a caving in or collapse will takes place. So this concept we derived from the earth pressure concept. So what we have understood is every soil has a natural slope. That slope is its own friction angle. Suppose if we have a sand in a lorry, if we are dropping it, it will come like this. So this slope is the friction angle. Naturally it will assume its own slope, that is the friction angle of the soil. Suppose if you want to increase the friction angle, that is not possible. That is possible only if we have a retaining wall or we have to reinforce the soil with some other materials like geosynthetics or geofibers. If we include a geosynthetics or geofibers, the friction angle will increase like this. So this can be demonstrated with a very simple and small experiment. If you have a sand like this and if you have a paper inside, there will be one friction angle, that is phi. If you remove that paper that is acting like a ring, it will slide like this. So this is phi 1. The phi 1 is the friction angle without any reinforcement called paper. If you remove the paper, it becomes phi 1. If it is the paper is inside, it is phi. That is the friction angle because of the reinforcement. This simple experiment shows the reinforcement of soil increases the friction angle. If the friction angle is increased, then the slope angle can be increased. If the slope angle is increased, the earth pressure coefficient will be less. The earth pressure will be less. So when we are designing a retaining wall for a particular height, if the pressure is so high, the best method is we can reinforce the soils. Because of the reinforcement, the lateral earth pressure can be reduced. This is also an advanced topic in soils where the soil is reinforced. We are studying the reinforcement of concrete. The reinforcement of soil is also a very latest topic, and this leads to the invention of geogrids, geosynthetics and all. Because of the geosynthetics, now the segmental retaining walls are being constructed, where the wall is having the same thickness from top to bottom. This is very useful when we are constructing the embankments in cities. For example, the retaining wall is having normally the shape like this. So the wall is having the more thickness at the depth and it is having a less thickness at the top. This is because the lateral earth pressure is so high at the bottom. In the segmental retaining wall, the wall thickness is the same. It is like this. This is possible because of the invention of geogrids or geosynthetics. So the technique is, the pressure distribution diagram is like this. So we are introducing geosynthetics. we are introducing geogrids at the intermittent layers, because of which the earth pressure is now cut at that particular point, and we have the tension is transferred to the lateral sides, and the wall thickness is the same from top to bottom. This construction of segmental retaining wall is a very, very useful technique in designing and constructing the embankments in cities, where we need not occupy the large area or the large land in the construction of embankments. In this session, we have discussed certain important topics in soil mechanics. They are the liquefaction, shear strength, lateral earth pressure, slope angle, and soil reinforcement. The liquefaction and shear strength are closely related, and it is related to slope angle, and it is related to lateral earth pressure, and all these things can be improved with the help of soil reinforcement. So the fundamental concept is, if we take water in a bucket, it will be like this. We cannot have a heap of water over the bucket. That is not possible, because water doesn't have shear strength. If we have a sand in a bucket, it can be taken like this. We can take the sand like this, but water cannot be like this. Water we can take only up to the top. The main difference is the liquids doesn't have the shear strength, soil is having a shear strength. Since the water doesn't have a shear strength, or liquids doesn't have a shear strength, Newton has classified certain liquids as Newtonian liquids, where it doesn't have the shear strength. But the soil is having a shear strength, so it is having a slope angle. So that has been related here. If the shear strength is there in soils, if it becomes zero, it will function like a liquid. It won't take any load. The lateral earth pressure is related to liquid in the sense the lateral earth pressure, horizontal stress as well as the vertical stress are the same, because it doesn't have a shear strength. But in soils, the shear strength is there, therefore the lateral earth pressure is different from the vertical earth pressure. Particularly if the wall is moving away from the backfill, it is less. So what portion or what fraction it is coming down, it was derived by Rankine using his plastic equilibrium theory, and there is an expression for Ka which we have explained. If the slope angle determines the Ka, that is 1 minus sin phi or 1 plus sin phi in terms of Ka, that slope angle can be improved with the help of a soil reinforcement. So this soil reinforcement is a very, very important topic, and in our college we have established a separate lab for soil reinforcement for geosynthetics testing. It is a geosynthetics laboratory which has been established with a partial financial assistance from the AICTE, and it is a unique laboratory available in our civil engineering department for the testing of geosynthetics, because this is a very advanced topic and very important one, and in case of practical applications. Thank you very much.